let's get started. It's my great pleasure to introduce Emma Brunskill. She is an assistant professor in the computer science department at Stanford, and she was on faculty at CMU before moving to Stanford. She leads the AI for Human Impact group at Stanford. She is a recipient of many awards, Best Paper Awards and early faculty career awards. Let's take the stage. It's my pleasure to have you here.
Thank you so much for the invitation. I'm really excited to be here. So I know for those of you that were in the last session, you just heard a lot about reinforcement learning. But I want to start, not everyone was there, and I know this is a diverse community, so I want to start with some of the reasons why I think this is such an exciting field. So I think when we think about sequential decision-making under uncertainty, it's really had an enormous legacy. It goes back to at least Aristotle, who talks directly about how do we reason when we want to accomplish something, that we think about the end result, and then we sequentially go back from that end result and think about how we could achieve each of the possible steps that is needed to accomplish that goal. And it's really amazing to think that about 2,000 years after Aristotle proposed this general way of thinking about sequential decision-making under uncertainty, that this was realized in a system that was made by Allen and Newell in the 1970s. So it's a challenge that we've been thinking about for hundreds of years, and that's because it's really an essential part of what it means to be intelligent, is our ability to think strategically about how we can accomplish the goals we care about. Now, this first slide talks about this in the context of where we know the outcomes of the decisions that we make. But of course, in many cases, we have to learn that from experience. So we have to learn about what might happen when we take different decisions, in many ways similar to how children try to learn about their environments. And it was really something that's captivated the computer science community since the 1940s, really the birth of computer science. Even people like Alan Turing were really interested in this question. But it wasn't until the 1980s that we started to see what we call reinforcement learning happening. People like Rich Sutton and Andy Barto and Leslie Kabeline started to think about this from an artificial intelligence perspective. And as we heard about this morning, people have also thought about this question from the controls community. But the majority of the way that I'm going to talk about it today is going to be looking at it through the lens of someone who cares about machine learning and artificial intelligence. Now, over the last 10 years, there's been this sort of amazing renaissance for reinforcement learning, and we've seen some absolutely spectacular results, particularly in the domains of robotics and Go, and other forms of video games or board games. And I think this paper by DeepMind is really incredible, and it talks about some of the ways that they've managed to accomplish sort of a world-class player for Go, which wasn't anticipated to be possible for a number of years. And it really drew on the insights of reinforcement learning. And I think this illustration of the hardness of the problem, this enormous branching factor, is really powerful. But perhaps not for those of you in this audience, but for when I talk to people in other contexts, a lot of people, when they've heard about all these successes, tend to assume that reinforcement learning is solved. That if we can tackle one of the hardest sort of intellectual challenges, things like Go, and beat humans at it, that it must mean that we're sort of close to something like general artificial intelligence. But I think to consider why I don't think we're close to that, I think it's useful to think about a parallel legacy of reinforcement learning. And that parallel legacy comes from thinking about reinforcement learning to benefit people. So similar from the very start, even though we've been thinking about how we can create robots and agents to play games for many years now, we've also been thinking about how we can create agents that help people learn things and how to use those for things like healthcare, customer recommendations, and other forms of applications that really involve directly interacting with people. And when we think about the distinction between these types of applications, there's a number of core differences that introduce new types of technical challenges. So if we think about stuff like interacting with a video game or Go or a robot, we typically have a simulator of the domain. And in those cases, we can afford to have enormous amounts of data to train. Our sample complexity can be extremely high. In addition, the stakes are fairly low. We can fail to play Go well millions or even trillions of times, as long as when we actually deploy the system, it's a good system. In contrast, if we think about how a system might interact with people, the data that we obtain comes from real people. We don't yet have really good simulators of people learning, of their behavior or their physiology, except for in rare cases, which means that we have to rely on real data, which means the decisions we make impact real people. And so that's really been the focus of my lab, is to think about how we can develop machine learning and artificial intelligence techniques to try to minimize and understand the data that's needed to learn to make good decisions. And I think of this both as being one of the core foundational questions of reinforcement learning, as well as having huge implications for us to be able to tackle the problems we care about. So in particular, the reason I care so much about statistical efficiency is that if we can learn to make good decisions faster, that means we can benefit more people. So what I'm going to do today is to talk some about some of the challenges that come up in this setting. And what I'm going to start with is a brief reinforcement learning overview, just to make sure that we all have the same notation, particularly for those of you that might be control theorists. So I'm going to use S to denote the state space, and I'm going to index that with T in order to denote which time step we're at. In the context of a Markov decision process, we think of the world as being in some state and having some policy that might be indexed by time, that is, it takes those states and returns an action. We then take that action in the world, and then we receive some form of reward. Now, if we think about sort of trying to quantify how good these decisions are, then we can think about this in terms of a value function, where we think about the immediate reward we get plus the expected discounted sum of future rewards. This implicitly encodes the Markov assumption that the state we have is sufficient to predict all future rewards independent of the past. And that's what allows us to write down this particular decomposition of the value function. The optimal value function is just going to be the maximum value function over all possible policies. And of course, in reinforcement learning, the challenge is going to be that we don't have an explicit model of the rewards or the dynamics model in advance, and so we have to be learning this through experience. Now, as soon as we start to have to learn this through experience and we care about statistical efficiency, then we want to be able to have formal ways to quantify how good our reinforcement learning algorithms are beyond their empirical performance. And again, I probably don't have to emphasize this to a theoretical community, but the reason that I care about theoretical bounds is that we want to be able to deploy these things with confidence in a variety of applications where we don't necessarily have access to a simulator. So probably approximately correct is a very common framework in many aspects of theoretical machine learning. In the context of reinforcement learning, we typically use the following definition. We think about the number of time steps where we're going to make a decision that is not near optimal, and we sum those up, and we define an upper bound on that as a function of the problem parameters. And our goal is that we can bound that the number of mistakes we make is upper bounded with high probability. Another very common framework, particularly for those of you familiar with the Bandit framework, which I know there are many experts in the room, is regret. And in regret, it's a little bit stronger of an assumption than PEC in many ways, because what we're going to do is we're going to judge the algorithm according to the difference between if it always took optimal decisions versus if it takes the decisions it actually takes. And this not only affects the immediate reward it gets, but it affects the subsequent rewards because the decisions that are made can lead to different parts of the state space. And so you have this sort of alternative life. Just like right now you're here listening to me talk, if instead you had went to go get coffee, that would have led to a different series of states. And in regret, you are judged relative to that first decision and all subsequent decisions. So we have these two very common formalisms for trying to evaluate how good a reinforcement learning algorithm is. And again, I just want to emphasize that if we can make progress on this, this can have huge implications. Because if we can get tighter regret bounds, whether in terms of their dependence on the problem parameters or in terms of the constants we can derive, then that can directly allow us to benefit more people because more people are getting better decisions. The other thing I want to emphasize is that while big data is really popular right now, there are many problems for which we will never have an enormous amount of samples. There are health conditions that only affect a small number of people. And so again, if we can have better algorithms for these cases, then we're going to be able to tackle these problems that could really benefit from these types of approaches. Now, we heard this morning about a lot of different ideas for thinking about the continuous state setting, or continuous state and continuous action. And I think that is absolutely the frontier we want to get to. I personally was really interested in the transfer learning setting because of the applications I care about. But when we were starting to develop these sorts of methods and bounds for the transfer learning and multitask setting, we realized that in fact the tabular setting was not fully understood. We didn't yet have min-max bounds for that type of setting. So we went back, and I'm going to talk about some of that related work now. So in particular, we're going to talk about a really simple setting, which is tabular episodic reinforcement learning, and try to understand that fully. So in this setting, the idea is that we're going to start off in some initial state distribution, sample a state from that, and then act for h time steps. So we're going to be in a state, take an action, get a reward, and repeat that for h time steps. And then the world is going to reset, and it's going to again sample initial state distribution, and we're going to act for another h steps. So this is the tabular episodic case because we're assuming that the state and action space are both discrete. And our goal in this case is to get a policy that optimizes the expected reward over h steps. Now, this setting, this reinforcement learning setting, is related but in some ways quite different than the common bandit setting, where we think about trying to just pick the best action on each time step. We don't have to think about the impact of our decisions on future states we might reach. And so quite intuitively, you might think that these two domains are separate. And in fact, a COLT open question that was posed last year was to argue that the hardness of learning in these settings should depend on the horizon. That if you have a longer horizon, somewhat intuitively, it seems like it should take you more data, or you should have higher regret terms, because you're learning to act in a longer horizon sequential process. And somewhat surprisingly, we can give a partial answer of no. That in fact it is not harder to act in long horizon problems in the sense that your regret bounds do not scale with h in the setting that was proposed in the COLT open question. And the reason that I want to bring up this particular result is that I think that the techniques to accomplish this highlight some of the recent progress that's been made in terms of trying to achieve strong bounds for this simple setting, which I think will provide useful foundations potentially for some of the other things we want to tackle. So again, just to recap, if we think about PAC and regret bounds, if we don't do anything smart in terms of strategic exploration, in terms of how we gather data, we typically suffer quite a lot, at least in the worst case. We can have exponential bounds for PAC, and we can have linear regret, meaning we can always make mistakes. Then over the last 10 to 20 years, there's been a lot of progress. I've only highlighted a few of the papers and sharing some of the work done by some of my students. And essentially during this, we have been able to achieve polynomial bounds for PAC, and we've been able to achieve sublinear regret. And at this point, these results are tight. So there was nice work by Mohammed Azir and colleagues in 2017 providing tight regret bounds for this setting. And we also have this summer provided tight PAC bounds for this setting for certain choices of epsilon. And so essentially this problem in some ways is solved. But I think that if we want to actually make these practical, then we would really like to be able to exploit problem structure. This is similar to what Wen was talking about this morning, that we know that there are some subclasses of problems that are much easier to solve in general. Bandits in general are easier than reinforcement learning problems. And so we would like to make it so that people could use these in practice and democratize RL. So you don't need to have a PhD in RL to decide what algorithm to deploy. And so as a step towards this, together with the student Andrea Zanet, we have developed instance-dependent bounds. And these are the bounds that allowed us to partially answer the COLT open question that I mentioned before. And I want to highlight sort of what I think the key insights were to go from sort of this exponential sample complexity and this linear regret down to this instance-dependent bound. So in the early work, one of the things that we often do is we try to bound uncertainty. We use a model-based approach, which we've heard this morning is often a very good idea. So we're going to use a model-based approach. We explicitly try to estimate a model of the environment, the dynamics, and the reward. And we're going to bound it. We're going to bound the difference between what we think the optimal value function will be under our expected parameters relative to the true parameters and the true optimal value function. And so when we think about this difference, one of the first ways people started getting polynomial bounds was to essentially use holders and use a Hofding concentration inequality. But the problem with doing that is essentially we're kind of doing a supervised learning approach. We're bounding the dynamics model separately, trying to get good bounds on that, and then combining it with a worst case bound on the value function. And so I think one thing that's led to a lot of progress over the last 2 to 3 years is to not do that and instead focus on the fact that what we care about is not obtaining good models, but obtaining good estimates of the value function. And so that means that instead of doing sort of a Holder decomposition, we can just bound this object together. And that by doing that, and then using a Bernstein-style inequality, we can get much tighter bounds. So recall h here is the horizon. I'm assuming that the reward is bounded between 0 and 1, which means that our value function is always upper bounded by h. If you use the first type of inequality, then you're going to automatically get sort of a h dependence in your resulting bounds. What the second bound allows us to do is to have h only appear in a term that is decaying much faster. So n is the number of samples. So that term is decaying much faster in this case. And instead, the term that is decaying as a function of 1 over square root n is something that depends on the variance of the next state value function. Now, intuitively, the variance of the next state value function looks at if you started in a state, take an action, and think about all the next states you could end up in. You want to think about the range of the values that you could encounter in that scenario. So if that range is really large, that's going to be a really hard problem to solve because the variance is large. But if it's really small or even deterministic, it's 0, it's going to be a much easier problem to solve. And in fact, this has been known experimentally for a while. There's this thing called environmental norm, and in this case, it's been shown that this can explain some of the hardness of when MDPs are hard to solve. So how do we use this? We can use this type of quantity and try to estimate it and use this in our algorithms. So we don't directly know this. This is a property of the actual domain. And so we don't know what the optimal value function is. But we can upper and lower bound it and maintain those and use those as reward bonuses. So in this case, in particular, we can look at something like where we take an estimate of the empirical transition and reward models. And then we also have a bonus term that depends on this upper and lower bound. And then we can use those to essentially just do dynamic programming to compute an optimistic estimate of the value function. We then, after getting that optimistic estimate, can also compute a lower bound. And we use the optimistic estimate when we actually decide how to act in the world. And for those of you who are doing bandits, you're very familiar with this, but for those of you who might not be, this optimism under uncertainty principle is extremely effective because either the world really is as good as your upper bounds, in which case you're achieving high reward or low regret, or it isn't, in which case you learn something. So what our bounds show is that this property of this sort of variance of the value function at the next state is in fact what appears in our bounds. And this is unknown to the algorithm, but our analysis shows that our algorithm is implicitly computing this very quickly in a way that allows us to have much stronger instance-dependent bounds. The other nice thing about this algorithm is it's still minimax optimal. So it both adapts to the structure of the domain, but also it still guarantees that we can match in the dominant terms the minimax results that we know are possible for the tabular episodic case. Now, we're not the first people to think about instance-dependent bounds. There's a lot of excitement around this area in general. In the tabular setting, there's been some previous work, but most of that previous work either requires you to know something about the domain, like give some domain-dependent structure, or it thinks about, has weaker guarantees, but for a harder case of the infinite horizon setting. But one of the things that I really want to emphasize about this result is that I think it just enhances our understanding of when is it hard to learn to act well. So it allows us to recover in the dominant term bandit results for this setting, for sort of tabular bandits, and near match minimax bounds for deterministic discrete MDPs, both of which are quite easy in many ways. If the world is fully deterministic, it's quite easy to learn. If it's fully stochastic, meaning that the actions you take don't affect the next state, it's also quite easy to learn. The hard case is when it's somewhere in between, when your variance of the value function of the next time step can vary a lot. I often find examples helpful, so I think an example of this is if you're trying to merge on a highway and you're trying to get out to the exit. And whether or not you get to go onto the exit depends on whether or not the person in front of you allows you to merge. So if the next exit is only a mile away, it doesn't really matter whether or not they allow you to merge. Either way, you're going to be able to get off the highway soon. If the next exit isn't for another 60 miles, it makes a huge difference whether or not they allow you to merge, essentially meaning that your value, the range of the variance of your value function in the next time state is hugely different. And in those scenarios, we're going to need more samples in order to learn what the right thing is to do. So I think that this is a really exciting time to think about exploration in RL. I think a lot of the papers we just heard about were really exciting, and at ICML there was also a huge interest in theoretical reinforcement learning. So I think the real questions to ask now are things about the size of the state space and the action space, and I think we're making really good progress on that. But I think also thinking about these foundations that allow us to think about adapting automatically to the structure and inheriting those bounds while still maintaining minimax approaches is really powerful. Now, this is assuming that we can actually choose how we gather data in the world. And in many cases, that's not always possible. And so the next thing that I want to talk about here is the counterfactual reasoning problem. So I first started getting interested in this about 5 years ago, and I was doing a collaboration with some colleagues at University of Washington on a game called Refraction. And Refraction is a game that teaches kids fractions by allowing them to split laser beams to fuel spaceships. And it's been played by about 500,000 students. And what we wanted to figure out how to do is how to adapt, personalize the game to individuals based on how they are progressing through the game to help them learn more and persist. So what do I mean by sort of personalization in this case, or how is this a reinforcement learning problem? This would be an example of a decision policy. Based on, the last action you gave them, which here would be sort of one part of the game or a level in the game, and how they did in that level and potentially past levels, then branch and think about which is the next level to give them in order to increase engagement and learning. And in this case, we were quite fortunate. We had access to about 11,000 students' data who'd been playing this game, and in that case, we had random data. So we were randomly giving levels over time, and we could measure how long they persisted, essentially how many levels did they complete until they dropped out. And our goal was to learn a policy that would maximize student persistence given that batch data set. So this is really an instance of counterfactual reasoning because we want to think about how well an alternative decision policy would do compared to the policy, or what I would call the behavior policy, that was used to gather the data. The behavior policy was random, and we want to think about how well alternative policies would do. Now, indeed, this sort of issue in counterfactual reasoning or causal reasoning is also becoming a really big area right now in machine learning. There's been a huge body of work thinking about causal inference from lots of different communities, whether econometrics or statistics, as well as sort of causal reasoning colleagues in computer science. But there's a lot of excitement right now of how do we combine those with machine learning methods so we can get to stronger generalization ideas. So in particular, if we want to formalize this, I would call this batch or counterfactual policy optimization, which is that we want to be able to take some data that was gathered by some behavior policy and be able to compute a new decision policy with the best expected sum of rewards when we deploy it in the future. So I'm going to assume that we have access to a data set D, some behavior policy pi B, which was used to sample the data, and then we want to be able to compute some estimate of the future value of an alternative policy. Now, one thing that you might imagine doing is doing something like the following, where we simply use some estimator to estimate the value of a value function under a particular policy, and then we take an argmax. So we have some policy class or model class or value function class, and we just do a maximum over that. But in fact, there's a lot of known failure cases for that, which maybe isn't so surprising. And in particular, even if those estimates themselves are unbiased, then the resulting argmax over that can themselves be biased, as we noted in a UAI paper a couple years ago. But in fact, this shouldn't have been surprising because we know from supervised learning that we want to do things like structural risk minimization or cross-validation so that we can pick classifiers and regressors that when we deploy them in the future are going to do well. And so what this sort of initial work on this fractions game led me to think about and led our group to work on is to really start on a quest for batch policy optimization with generalization guarantees. And I think what we would like to get to, which I don't think we're close to yet, is something like the following. That you would have some set of hypothesis spaces, and you would like to be able to think about policies that lie in each of those spaces. and try to compute the policy which has the best generalization guarantees going forward, which I imagine would be some combination of its empirical performance as estimated with your existing data set D, minus some quantity that likely depends on the complexity of that policy class, as well as the amount of data that you have. So this is something that would look sort of like structural risk minimization, and I think if we could do this, the number of applications we could tackle would be incredible. Now, we can think about each of these sort of parts. The first part we can think of as being policy optimization. The next part is essentially policy evaluation. And the last part is error bounds. And I just want to highlight here that I think there's all sorts of really hard complexities compared to in addition to the ones that we normally try to see in structural risk minimization. And one is that even the choice of the hypothesis class, even what we mean by that, there's a number of choices in the reinforcement learning setting. So in reinforcement learning, we can think about there being dynamics models and reward models, sort of classes of MDPs. We can think about there being value functions, and we can think of there as being policy classes. And so already, even just making that distinction, there's an enormous number of different ways we can even define what a hypothesis class here is. So as I said, I don't think we're close to being able to solve this yet, but I'm going to tell you about two different ideas that we had recently over the last few years to try to tackle aspects of this problem. And the first is looking at policy evaluation, which is a critical part of this issue. Now, there's an enormous amount of literature on the idea of policy optimization from observational data. This comes up often in the guise of treatment effect estimation, particularly in healthcare and econometrics, but most of this literature has focused on one binary decision. And in reinforcement learning and many other settings, we're really interested in sequences of decisions. And I think the reason why that introduces additional difficulties is conveyed really nicely by some of my colleagues' Nature Medicine paper recently, where they're thinking about some of the pitfalls and challenges for doing reinforcement learning in the healthcare setting. And so what you can see here is that if we think about having a behavior policy that's used to gather data, then it is generally going to take different decisions than a new policy we might want to evaluate. And those different decisions are going to lead to different state distributions. So if we have a sort of a cohort or we have a set of data, and let's say we want to think about a policy where we first do some sort of ventilation. So only a subset of the patients may have had ventilation done at that stage, so that's going to reduce the amount of data that we have. And then let's say our policy would say that we would apply some form of sedation. And then at that point, again, we're typically going to lose a further amount of our data. And so we have this sort of data attrition that is going on over time because our data generally will not look the same as what it would look like if we were to execute a different type of policy. And so one of the first questions we thought about in this space is to think about how do we do sort of more data efficient estimation by using biased estimators. So when we think about doing counterfactual reasoning for policy evaluation, we could take many different choices, particularly in the one-time step setting. And one approach is to use parametric models. And parametric models, whether they're of the dynamics model or of the value function, are great in the sense that they're low variance, but they're typically going to be biased unless we can make a realizability assumption. And I think the realizability assumption is challenging because we often just can't verify if that's true. So an alternative approach is to use something like importance sampling, which doesn't need to make this assumption, which is unbiased under some standard assumptions, but it often can be very high variance. It suffers from this problem of sort of trying to match data to the distribution you care about. And so in statistics, the doubly robust estimator tries to combine between these two to sort of get some of the best of both worlds. And people like Miro Dudek and other colleagues brought this over to the reinforcement learning and AI community over the last 5 to 6 years. But in doing this, they often focused on unbiased estimators. And so in our work with my former postdoc, Phil Thomas, we were interested in whether we could introduce some bias strategically in order to save variance. So that if we were really caring about this policy evaluation setting, that we might be willing to do this trade-off. And in particular, we introduced 2 different types of estimators. And in one case, essentially, we're just blending between 2 of these. We have these trajectories, which are making sequences of decisions, and we can think of estimating the reward of part of the trajectory with a model and part of it with an importance sampling estimator. And so then we can do a quadratic program to try to directly minimize the estimated bias and the variance. We can also introduce a weighted doubly robust estimator, which is much simpler. Essentially, we're just normalizing the weights. So the nice thing about both of these is that they're both biased, but they're under minor assumptions, they're still asymptotically consistent. So how well do they work? What does this bias? Well, we did a grid world simulation just to sort of illustrate the differences between these approaches. What you can see here is we have some existing data collected from one policy, and we want to evaluate the value of a different policy. And on the x-axis is the number of histories, so essentially how much data we have. And on the y-axis is how well we can estimate this alternative policy if we were to do something different in the future. And the thing that I want to highlight here is that if you look at our new types of estimators, they're needing only about 10% of the data in order to estimate the same accuracy of the policy. So they're just about 10x more data efficient. And I think that's important, and I think that that's illustrated by some subsequent work from some of our colleagues, where they are thinking about trying to use sepsis data and trying to understand how to do better sepsis treatment. Sepsis is a huge problem. Many individuals, it can also have a high mortality rate. And so figuring out better decision policies and if AI can help is an important question. It's also something where we have some historical data that is possible to look at. So some other colleagues of mine looked at the case of how could you learn from prior data from about 20,000 patients better treatment strategies for sepsis. And what they did in this case is they tried to compare a number of these different forms of estimators for off-policy evaluation. And what they found in this case is that our weighted doubly robust estimator that Phil Thomas and I introduced was the only consistent off-policy estimator of the ones they tried, which could reliably detect that the new proposed policy was going to be better than the existing physician policy. So that's important because if we can be more statistically efficient or we can be more accurate with the data that we have, we might be able to more reliably detect that something is better and give us confidence in actually being able to deploy it and make things better for patients. Now, I want to caveat this with an extremely important caveat, which is our estimator, and almost all of these estimators, make a very strong and almost definitely wrong assumption, which is there's no confounding. And what that means is that the decisions that are made by physicians or others can be completely predicted from the state variables we have access to. So that means that, if they smell that someone is smoking and they use that information to make a decision and they don't write it down, that is an instance of confounding that almost definitely will impact the types of estimates we make. So one of our new efforts right now is to trying to think about how do we address this sort of challenge, which I think is a huge issue in terms of being able to really use observational data. So that caveat aside, I think that this shouldn't be thought of as we found a way to better treat sepsis. It should be thought of as there's real differences in how data efficient these different evaluators are, and that those differences in data efficiency could allow us to be able to either answer or not answer different questions about how we can actually deploy things effectively. So the next thing that I want to talk about is this is one idea of how we can introduce bias to try to tackle this policy evaluation question. Another question that is critical for us to move towards structural risk minimization is how do we do policy optimization? What thing are we actually going to deploy? And I think one of the really big challenges here is not that we don't necessarily have lots of ways to try to do policy optimization, but that I don't think we have very good error bounds. So I think we're in the really early stages of trying to be able to do all of this together. There's some nice results that we heard about earlier and that other colleagues have been doing, but I think that there's still an enormous amount to go. For example, if we look at sort of importance sampling estimators developed by Phil and others, they typically struggle in the sense that they both don't sort of explicitly rely on the structure of the policy class you're optimizing over, and they typically require an enormous amount of data. So if you're someone like Adobe or Amazon or Google, I think these estimators can be completely reasonable, and in fact they have been used in some of these contexts. But I think if you're looking at observational health, there's something where you might only have thousands, not millions or billions of data points. I just don't think those methods are going to work yet. Similarly, there's been a lot of work on fitted Q iteration style bounds from sort of 2003 onwards. There's some really beautiful work in this setting, including from people in the audience. I think one of the limitations here is that they often require much stronger assumptions on realizability. And the challenge is that if your function class is not sufficiently expressive to capture the policies and the optimal policy, typically the bounds require on something that is uncomputable, which means that we can't directly use these to then get bounds that we could make decisions about. So what we'd really like is something like this, and what I'm going to do is I'm going to move the goalpost. So I'm going to say, this seems wonderful and really hard, and we want to get there, but can we make some progress by thinking about a slightly simpler objective? And so one alternative would be, instead of trying to get strong generalization guarantees on the actual performance of a policy, can we just guarantee that we could find the best-in-class policy? So we have a set of policies. Policy Gradient does this all the time. There's a huge amount of progress right now and interest in using policy search techniques where we just try to find the best policy in a class. And what I'm interested in here is, can we do that also in the offline batch setting where we just have access to an existing data set? So we'd like to be able to solve something like this, and maybe the types of guarantees we would want would look something like this, where we'd say there's some performance of the best policy in the class, and we would like to ensure that the policy that we return in the class isn't too far off from that. And maybe how far off from that is, should depend on the sort of VC dimension of that policy class, as well as how much data we have. So that's the sort of style of result that I think would be nice. And then we sort of don't know that this is optimal, but we know that we're doing pretty close to the best that we could do, and we have an understanding of the rates at which we're converging towards that best in class. So we now have, to my knowledge, the first guarantees of this type of result. And this was led by a terrific student, Xinquin Ni, as well as my colleague, Stefan Weiger. And this is for a particular subclass of settings where we look at when to treat policies. And I put up the result, the style of result we have, which does exactly this of saying, how far are we off from the best policy in the class? And that depends on the sort of complexity of the policy class and scales as roughly of 1 over square root n, where that's the amount of data that we have. So what do I mean by when to treat policies? So when to treat policies are going to be processes where we sort of keep going till at some point we make a single decision. And that single decision could be one of a finite set. So we could hold a stock for a long time and then decide to sell it. Or we could not treat a patient for a long time and then decide one form of treatment. As an example, and we're going to think about all of these as being parameterized because we're going to be doing a policy search approach. So as an example, we could think of something like a linear threshold policy, where we're going to start HIV treatment as soon as CD4 count dips below a certain threshold. And we want to search over what that threshold is and which is the best policy in that linear threshold class. Or similarly, we could think about sort of a health, trying to keep health above some particular metric, and then we could think about when we dip below that, then we change the treatment in that scenario. And I want to highlight here that I think one of the many interesting benefits of thinking about this scenario is that it's a nice way to put in interpretability and problem structure. Because, for example, if we're communicating with doctors and we want them to consider using these policies, then being able to be interpretable and to inject domain knowledge about what classes of policies are reasonable can be really powerful. And the policy search techniques allow us to do that directly. Okay, so how do we do this? How do we select which of those how do we do that policy search? There's kind of a couple key ideas. The first is we're going to use an advantage decomposition. This is simply a way of representing the difference between the value of a policy we care about and an alternative policy, in this case, the policy that never treats. So we're going to think of there being a never treat policy and then a new policy we care about, and eventually we're going to want to take a maximization over all these alternative policies. And this decomposition was introduced by Shyam Kakade, as well as Susan Murphy considered this as well in a different context. And essentially, it just allows us to write down the value function in terms of a series of advantages, a series of differences of the expected value if we were to stop and treat right now with a particular decision versus if we were to wait one more time step and make a decision then. And the nice aspect about that is that it's just a one-step treatment estimation problem. So in some ways, we've reduced the problem to a bandit now, and we can leverage a lot of the insights that have been done for off-policy bandit estimates. And in fact, that's what we do. So we use R-Learner, which was a previously proposed one-time step treatment estimator, to help us estimate these sort of advantages when we're summing them up. And So we do this, and we do this in a doubly robust way, so that we need to do this from data. So we assume that our data is collected by a behavior policy, which has to have some amount of randomization in when people are actually treated. Otherwise, we couldn't estimate the alternative. And so we use that data, and we compute a doubly robust estimator just for those advantages, and can combine them in different ways in order to do the policy optimization. I think one of the things that was really exciting to me about this work, as someone coming in from an RL perspective and collaborating with statisticians, is it allowed us to think about some of these new ways that Max was also mentioning earlier today for trying to do this type of estimation with semi-parametrics, where we think about there being nuisance parameters, which in this case is going to be the behavior policy probabilities of whether when would the doctor take this decision or not. Often we don't have access to that, but we can estimate it, as well as the value function itself as only being a nuisance parameter that we're using to try to get us to the goal of being able to do treatment effect decisions. So that's the style of approach that we took in this case, and it turns out that it can also have some nice benefits, at least in the simulators we've looked at initially. So for example, in this case, we were thinking about how do you keep a health metric above a certain level. And we assume that we get to see the state plus some noise, and we compared our approach, which is ADR, Advantage Doubly Robust, to IPW, which is an importance sampling style approach, or fitted Q. And on the x-axis here is the amount of behavioral data we have, and on the y-axis is the difference between the policy that our approach output, or any of the approaches output, versus the optimal policy in the class. And so lower is better, and what you can see here is that we're scaling very nicely as we get more data, versus fitted Q iteration is not doing as well, and importance sampling is going much slower. And that, in fact, is one of the benefits of these styles of techniques, that you can have approaches where you can be estimating these nuisance parameters at much slower rates and still are able to get sort of square root n rates for the things that you care about. Just to illustrate, because it may not be intuitive, the reason why fitted Q iteration here may not in fact go down ever is because this is a biased estimator, and you're going to be constrained by the function class that you're using. The other thing that I want to highlight here is that the policies that returned are not always interpretable. So ours is shown on the left, and the fitted Q iteration is shown on the right. So here we have a linear threshold policy, and we've constrained it to be that. So we're doing policy class search over a linear threshold, which in this case is a combination of the health metric and the time step. So we will find sort of a linear threshold so that at some point we will turn treatment on or turn treatment off. And that's nice and interpretable, and we can compare that to what the optimal was in this case, which for this illustration, it was very close. And this is something you can imagine showing to a decision maker. In the contrast, something like fitted Q iteration directly represents a function over the value function. And it tries to optimize over that space. And that means that it can result in a policy that is not very interpretable. So if you were to show the second one to a decision maker, I think it can be quite unclear, because even for the same time step, even for states that are quite close together, sometimes you're getting kind of flickering between what is the right decision to make there. And it's not obvious whether that's due to sort of finite amounts of data, or if that's really due to the function approximator that we're using. And so I think that there's a lot of benefits of using policy class optimization. So I think that we're still in the early days for this quest. I put up a few of the papers that we've been working on to try to deal with policy optimization, policy evaluation, and error bounds. And there's also been some really beautiful work that's going on with a bunch of my colleagues. But I want to highlight that I think that we're really in the very early stages of this. And to me, some of the most exciting things that are in the frontiers for this is to think about relaxing some of the common assumptions that are used in our proofs and almost all the other proofs I know of in terms of trying to get any theoretical guarantees. And these type of assumptions are both the non-confounding issue that I mentioned before, but also things like interference, that when you are making decisions for one trajectory, that is not affecting another trajectory. Now, in some cases, that might be very reasonable. But for example, I was hearing a nice talk by some people at Uber recently who were talking about if you do an intervention for a subset of drivers, drivers talk to each other, and so quickly you'll get bleed over effects. And so you can't always assume that the decisions made at one time step or for one trajectory are independent of the decisions and outcomes that are being made in other trajectories. And so I think there's a number of different common assumptions that force us not to be able to tackle some of the cases we'd really like to be able to tackle, and also introduce really exciting theoretical questions for us to look at. But despite sort of, some of that, the enormous amount of work that I think is still to come, I think that there's a lot of reasons for optimism. And I want to go back to the example that I showed at the beginning, which is to talk about, how could we optimize for students going through this fractions game? And what we found in this case is that we could do this sort of batch counterfactual learning, in particular relying on importance sampling techniques, to estimate that we could find a decision policy that would increase persistence by 30%. And so we could get an estimator that would estimate that, and then we ran an experiment with another 2,000 students to actually verify that was the case. And so this is the first example that I know of doing off-policy batch reinforcement learning and really showing that for students that this can lead to a benefit. And so the cool thing about this result was both that we predicted it would be 30% improvement. It actually was about 32% improvement, meaning that we did accurately estimate the improvement that we were going to observe, and B, that there is potentials for huge lift in terms of using these types of techniques to improve decision making for some of the applications we care about. So just to summarize, I've talked today about some of the different techniques to minimize and understand the data that we need to learn to make good decisions. I think that both exploration and how we gather data smartly is a critical part of that puzzle, as well as how we use any data that we have collected to try to make better decisions in the future. And so a natural open question, too, is to think about, well, can we combine these two together? And does doing so lead to additive benefits or even multiplicative? And I think that we have some very preliminary work to suggest that combining them together can be beneficial. So we have an ICML paper this year that suggested that we could both do better exploration by doing off-policy evaluation and get tighter bounds on our off-policy estimates because the policy we were executing was a particular strategic exploration policy. So again, I think we're in the very early days for that, but I think that's also a really exciting area for future reinforcement learning. And I just want to summarize once more that I think if we can do this, if we can figure out these better techniques in order to learn to make decisions faster, then that has huge potential. Not only will we be able to answer some of the really cool questions and frontiers of reinforcement learning, but I think we'll be able to open up this enormous set of applications that could really benefit from reinforcement learning. Thank you. Questions? How it works? Yeah, so the question was for this result I mentioned at the end of if we bring together exploration and counterfactual, how does that lead to a benefit? The intuition is that normally when we're doing off-policy evaluation, we don't know anything about that policy. But in this case, we know that it's an approximation of the optimal policy and the optimal value function, and that is not a random quantity. That does not depend on the past, and it doesn't depend on how you're gathering data. And so we leverage that fact to do a decomposition so that we end up with tighter confidence intervals by leveraging the fact that the optimal policy and the optimal value function, while latent, is static. Yeah.
The linear threshold result, this is agnostic. Like you're competing with the best linear threshold policy. You're not assuming that
Correct. Yeah. So actually, his question is, what was the results for the linear threshold policy? We're not making any assumptions of whether or not that's a good policy. We're only competing with the best in class. But I think that, and so yes, it could be horrible. But you could imagine nesting this with a model selection. So you could be doing this for different. We're not restricted to linear threshold policies. So it's all for just any policy in the class. So you could be doing model selection on the outside of it. But if all of your model classes are bad, then you're in trouble. Yeah, when? Yes. So the question was, why does the horizon not appear in the bound? Let me see if I can go back to it. So the intuition for this is that in the original conjecture from last year, it's a slightly different. So I mentioned that the reward is bounded between 0 and 1 for most cases that we think about and most cases people have talked about, which means that the range of possible value functions is between 0 and h. In the conjecture, they said, let's get rid of that because that's sort of just a normalization and scaling. So we're going to assume that all value functions are bounded between 0 and 1. regardless of the horizon. And in that case, does H still appear? And the intuition is, let's see if I can go back, is that means that the maximum reward that you could get is only 0 and 1, and our bounds scale with that. So let's see if we can get to there. Okay, so here our bounds scale with, we get the minimum of two things. We either get the minimum of the max variance of the value function at the next state, or the square of the possible sum of rewards you could get in under any policy, under any trajectory, divided by H. And that for us is going to be bounded. So we end up getting 1 over H there, and that cancels with the T, which is K times H. Yeah. It's a great question. Yeah, the question was, are we really assuming that the world really is an MDP, and would that be reasonable? So I think that in some of our results, I did not say some of the technical details. Some of our results don't require Markov assumptions, and in particular, the works with Shinquin and Stefan don't require the world to be Markov. So we're not making that assumption there. I think in other cases, we should mostly think of it as like a structural assumption that ideally we can bound the error from that, because I completely agree. It's often not going to be Markov for the real setting. Though there's some interesting questions. One of my new students is very interested in the health side, and so he was saying some of the ways that that doctors interact with medical record systems may make them more Markovian, in the sense that the interface design may only show you the most recent lab results, which can increase Markovian-like behavior. And so we're quite curious to look in some of these cases to essentially do imitation learning to understand, is the policy people using looking Markov or looking, like they're using the full history?